Video focuses on simplifying radicals. Here is the definition of a radical's pieces. The first thing is you have your radical sign. The next thing you have is your stuff underneath your radical sign, which is called your radicand. And then there's this little number in front of the radical sign, which is called the index. Now, if there isn't a number there, then you have to assume that's what we call a square root with an index of 2. Here is a review of perfect sheet. I would take the time and write down these perfect squares, cubes, fourths, fifths, a minimum of these. You may want to add to this list. It's going to make your life a lot easier over the next few days and in the future if you know your perfects. So let's start off with the perfect squares. With your perfect squares, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. You can scroll that down. I just went to 10. Again, you can make that list longer. So go ahead and pause if you need to. All right, now let's go to the perfect cubes. These are the ones you're going to use to simplify if you have a cube root. So 1 times 1 times 1 is 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, and so on. I just went up to 6 cubed. Again, definitely you can add to that. This next list is when you have powers of 4 and you're simplifying with a fourth root radical. So 1 times 1 times 1 times 1 is 1, 2 times 2 times 2 times 2 is 16, etc. All right. Last one, I just did a few here. These are our powers of 5, so you're simplifying things that have fifth roots. So 1 to the 5th, 2 to the 5th, 3 to the 5th, you can see those answers. All right. Now let's go ahead and simplify some radicals. So the first example, how you say that first example is the square root of 16. Notice there's not an index here, so that is a square root. So I'm going to take my time on this problem. These problems are going to go much faster than I'm showing you right now. You're looking for a perfect for 16. So if we go back here to our 16, and remember we're looking, this is for our square root. Here's our 16, so we can break it down as 4 squared. So I'm just going to break down 16 as 4 times 4. Now how this works is if you have the index of 2 and a power of 2, everything cancels out except for that base of 4. So your final answer then is 4. How we say this is the square root of 16 is 4. All right, the next one, 18. How you say this problem is the square root of 18. The index is not there, so it's a square root. Let's go back to our perfects. If we look at that, here's 16, and we jump to 25. So this is not a perfect square number. So instead, we're going to break it down to possibly get a perfect square. So we're going to use this thing called prime factorization. We're going to break down 18 into a product of 2 numbers or more. So I'm going to just start with the number 2. And I'm going to say, does 18 divide by 2? Yes. It divides by 2. That gives us a 9. So now we have 9 times 2. Now let's go to our perfects. Is 9 a perfect? Yep, right there with 3 squared. So I'm going to separate this out. As 2, 3 squared, and then 2. Now, like I said in the last example, if your index and your power match up, then what you're left with is just the number 3. Now what's going to stay underneath is anything that's not raised to a minimum of 2 powers. So this doesn't have a 2 to the second. So that's what I call my leftovers. So that's a 2. If you want to throw the index in, you can do so. You don't have to with square roots. All right, let's go down to the square root of 20. Square root of 20 is not a perfect, so I'm going to break it apart. So I could break it apart as 2 times 10. That doesn't help me as much as 4 times 5. So if we go back to our perfects, 4 is a perfect with 2 squared. So now I'm going to break apart 4 as 2 times 2, and then I have 5 left. So now my index and my power match up here. So that 2 is going to come out. And now, do I have a 5 squared? Nope. So that stays underneath as my leftover. So it's 2 square roots of 5. All right, let's jump down to 135. 135 is not a perfect square with anything. So if I started with just trying to divide by 2 with 135, I don't get a nice number. So let's try dividing it by 5. I get 27. So let's just start with 5. So here's my index of 2. I have 5, and then I get a leftover 27. So 5 is a prime number, so let's continue with 27 and breaking that apart. So I'm going to break apart 27 as a product of 2 numbers. I'm going to do 9 times 3. I'm going to go one more time. Five, and now I'm going to break apart this 9 as 3 squared, and then I have this number 3 left. All right, do I have a perfect square in there? Yes. This 2 and this 2 match up, so we're going to bring out a 3, and then what stays underneath is everything that is not raised to the second power. So this 5 and this 3 will stay underneath. Now, can I combine that 5 and 3 back together? Yes, that's square root of 15. 5 times 3 is 15. Then I have this number 3 left. So there's my final answer. 3 square roots of 15. All right, now I'm going to add some variables in for you. So let's break apart 75. The square root of 75. 75 is not a perfect, so I'm going to break it apart as 3 times 25, and then x cubed. Then 3, I can break down 25 as 5 times 5, and I can break apart x cubed as x squared and an x. Why I'm breaking it down into powers of 2 is because my index is a 2. So this is, oops, that should be a 5 squared here. Alright, so there's my number 2 here, my number 2. So those 2 pieces go out in front, 5 and an x. Because the square root of 25 is 5, the square root of x squared is x. The things that stay underneath are things that are not raised to the second power. So my leftovers then are 3 and x. All right, going down to the square root of 245, x squared, y to the 4th, z. All right, I'm going to start with 5 again, the prime number 5. 45, if I divide that by 5, I get 49. And 49 is a perfect, so 5 times 49, x squared, y to the 4th, z. Then I have 5, 49 is 7 times 7, x squared. And I'm going to break down that y to the 4th as y squared and y squared. and then I have a z. All right, remember my index, anything with a square root is index of 2. So where is my 2's? Right here, right here, right there, right there. So those 4 things are going to come out in front of the radical. The square root of 7 squared is 7. The square root of x squared is x. The square root of y squared is y. The square root of y squared is y. And now my leftovers are my 5 and my z. So they will stay underneath. Now let's just clean up that y times y, and we get y squared. And then times 5, square root of 5z. All right, moving on. Cube root of x cubed. Just variables now. So I'm going to change that to x squared and x. My index is 2. So here's my index, and there's my power. So that's going to come out in front as an x. And then this little x will stay underneath as a square root. So x square roots of x. All right, what's different about this problem is we have a negative. I'm going to leave that negative there. I'm going to break down x to the 7th as x squared, x squared, x squared, x squared. Oops, that last one should be x to the 1. All right. So my index is 2. So this term, this term, this term come out in front. Leftovers of x. Now let's clean up that blue piece. Negative x times negative x times negative x is negative x cubed. And then you have the square root left. All right, square root of 25x. 5 times 5 is 25x. So what's coming out? A 5, left over, an x. Next one, a squared, a squared, a squared, a squared, a, b cubed, oops, b squared and a b. All right, so this a, and b come out. So you have a to the 4th and a b. And then what's your leftover? This a and b. Hopefully these are going a little bit faster here for you. All right, we've talked all about square root, square root, square roots. Now we're going to jump into a little bit higher power. Now we're talking cube root. So we have to have things breaking down into powers of 3. So x cubed, b cubed, b cubed, b cubed, to a total of 9. My index is 3. So index and power match up, so that x is coming out. Power, 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 1, 2, 3. So that becomes b cubed. No leftovers. Last one, 27 can be rewritten as 3 cubed. A to the 6 can be rewritten as a cubed and a cubed. And then b to the 12 can be written as b cubed, b cubed, b cubed, b cubed. So what comes out is a 3, an a and an a, which is a squared, a b, a b, a b, and a b, which is b to the 4th. There's your final answer.